Welcome to the Python ARM Radar Toolkit extremely short course. I'm the science lead, everyone knows me, I'm Scott Collis. Jonathan Helmus at Argonne National Lab is the development lead who is actually responsible for most of the coding and actually making all this stuff work. Greg McFarquhar said he actually wanted to be here at this course and said, don't worry, I'm going to learn about Python when I'm across in Australia. I kind of think he had the wrong idea. But so this isn't about the snake. This is actually about the language, not even about the comedy group of movies, what it was actually named after. So this course we're going to be using something called the Ipython Notebook. The Ipython Notebook, very simply, is a Python kernel, a Python instance running on your machine that creates a server that you then point to. It actually allows for very nice interactivity with the language. It's actually the standard way I develop my code at the moment. I will run it, develop it, investigate it on the Ipython Notebook and then cut and paste into a text file for my final actual script. We're going to step through those steps today, but before we start I just wanted to give you a grain of salt. This is the first ever PyART course that we've ever run. This is an aspirational course. 1 hour is very short. Caveat, caveat, caveat. We have 3 notebooks that I've put together for this course. I hope to get most of the way through 2. The third one is left there for an exercise at home, because I know a lot of you are really interested in gridding and doing whole volume analysis. That's what the third one actually covers. The first 2 is an introductory notebook to the actual how radar data looks like in PyART, and the second one is all about plotting RHIs and actually doing some basic analysis in radial coordinate space. Just before we begin with those, I wanted to point you actually towards where PyART actually resides. This is the launching page for PyART. I'm going to send you, if I already haven't, I'll send you another email at the end of this course with all these links in there, so don't bother writing them down. The actual code exists at this Github repository. Github is kind of like Facebook for code. It actually allows you to interact with the code base as well as just downloading it. So if you guys like what you see today and you're interested in keeping in contact with the project, I highly recommend you sign up for a GitHub account and click on the watch. Actually, it says unwatch here on mine because I'm already watching it. Click on the watch button. If you ever have any issues with PyART, click on the issues button and you can submit a new issue and actually point out where the error is. You can even go into the actual code and tag the particular line you're having problems with. You can dump images in. We watch this very, very closely, and as you can see, we have very, very long conversations with various people about all these fun things and what we're discovering in them. And as you all become gurus, eventually, we can't really cover it in this course, but we'll show you how to actually contribute code to it. PyART has about 5 active contributors at the moment, 13 total contributors, and we don't even know how many users at the moment. It's gaining a lot of traction. So what is PyART and what isn't PyART? Well, first of all, okay, let's actually get to getting people up and running. So who here, I know some people had some problems getting it running. Most people have at least been able to look at the notebooks and have downloaded the data. So, Marcus, yes. Can you give Sandra a hand? Yes. I think Sandra, do you manage to get the notebook up and running, no, Sandra? I got the notebook, yeah. You got the notebook up and running. Excellent, yeah. Excellent. I don't. You don't. Marcus, do you have the data downloaded? Yeah. Yep, okay, cool. So Marcus can work with that. So, again, we're going to run through a series of exercises, demonstrations on the Ipython Notebook today. So if you look here now, we're able to see this. Let me actually make my font a bit bigger so people can actually see where I am. So I'm actually in my terminal or my command line, or whatever you're using, your shell on your computer. I am actually in the directory that has the notebooks in it here. So, so you downloaded the zip file, it expanded out to notebooks, ASR_PI 2014. If I look at the contents here, I have my data files all in the same directory. This just makes it easy. You can add a directory later on. And I have these .ipynb files in there. to run the notebook, it says Ipython Notebook, 2 words. And that then will actually start the server on my machine running on localhost and point my browser to it. And what you end up seeing inside this here are all the notebooks in that current working directory. As I said, we have 3 notebooks. These are not in the order we're going to look at them. We have investigating the PyART radar object, plotting and signal-to-noise ratio, plotting PPIs, CFADs, and mapping. So we're going to start with plotting and SNR. So I'm going to give people a second to get that up and running. When you get it up and running, go to Cell, All Output, and hit Clear. That will actually clear all the output. And once everyone's up to there, I'll actually kind of start stepping through and describing the notebook. Except for the people who walked in late, the people who are here at the beginning, is anyone behind or having issues with that? You have a variety of cells. If I double click in that top one there, this is what we call a Markdown cell. I can click the difference between code and Markdown. And so a Markdown cell is simply HTML markup, LaTeX, whatever you want to put in there. Think about this as a laboratory notebook. I could write a whole heap of cool equations in there, then put the code underneath it that actually mimics those equations actually in the code and does the analysis. So to execute a cell, I'm going to turn this into code and force an error out of this. You hit Shift, Enter. And of course, because this isn't actually Python code and it tries to run it, I get a syntax error. I get the output of the cell above in the line below. So I'm going to go back here, turn this back to a Markdown cell, and hit Enter, and then it will nicely format. Okay, some big differences between Python and other scientific environments. Python, when you load Python, you get bare bones Python. It isn't actually a really good scientific environment at all. You need to import the modules you want to use. This is good for a variety of reasons. One, it's very quick to load, and 2, it doesn't clutter up what we call your namespace. I might have 2 versions of the same module. I don't want all the variables and all the function names overwriting the other. So you actually have to explicitly import functions here. So this line here, I import PyART. From the matplotlib library, I import the pyplot function as PLT. And I import numpy as np, and this final line in there, that's actually an Ipython command telling the notebook to do all the rendering of my graphics in line. Rather than trying to save them off to a separate graphics, put the graphic below the cell that runs it. So everyone can point there, hit Shift Return. See the little asterisk that came up next to in there for a second? That's telling us that that line is actually running. When that asterisk goes away, that line has run. Now, has anyone come to a cataclysmic halt?
Just do me a favor, go through that again slowly. You clicked on.
So I'm in the cell at the moment.
Yes.
I hit Shift, Enter.
So in any other way, is there like a...
Yes, there is. You can go up to Cell and hit Run.
Okay, so that will do Shift Enter will execute everything in that.
In that cell, in that block. In this block.
So how do you know if it did it?
You won't get an error, or you get. So, for instance, if I go down here, one thing you can do is I'm going to put a print command in there. Print, done, and now I can see I get the output down below there.
Okay.
So the next cell here, we're just pointing PyART at the data here. If you put the data in the same directory which you're running the notebook from, you can leave this data string as just being an empty string. If you put your data in another directory, like /users, Collis, data, something like that, enter that in there. We're going to add those 2 strings together here to create a fully qualified file name. So execute that cell there. And then what we can do here, to create a new cell, you click this little button up here, right next to the play button. That creates a blank cell underneath it, and I can type into this cell print FQFN there. And I can see my fully qualified file name there.
How do you, so can you delete that cell if you don't want it there?
You can, what, delete a cell?
Yeah.
Just go. You can see the scissors
click,
button
I'll
there?
cut it, okay.
Exactly, just cut it out. So the next line here is where we actually start using PyART. So radar equals pyart.io.read, my fully qualified file name. That puts all the data from whatever file I'm using. Now it could be CF Radial, MDV, Sigmet, UF, NextRad, and a bunch of others. Anything that RSL reads, plus a couple of other file types in there, and it puts it into what we call a common data object, common data format that is the same independent of the file source. So this first tutorial is going to identify and investigate what this data model looks like in Python. So a data model is just how a particular data structure is stored in memory, and then how that memory block looks like in the various variables and objects that you use within a programming language. Could be strings, records, integers. We make very heavy use here of a Python object known as a dictionary. A dictionary is just simply a string addressable list. If I have a list and I say print my list 0, I get a number or something out. Print my list 1, I get something out. Instead of using 0, 1 and 2, we might say print address Bob in there, and we get whatever's in that container out. What it allows for very nicely readable code. So everybody execute that line. Radar equals pyart.io.read FQFN. Should run fairly quick. Reading in from CF Radial is nice and quick. And now we're going to actually have a look at what is inside our radar. So within our radar object, we have a variety of metadata and data. All the data, all the moments, reflectivity, radial velocity, whatever, is actually stored in radar.fields. Radar.fields is a dictionary, and there is a method, and a method is simply a bit of code in that object you can run called keys, which tells you what the various addresses are inside that dictionary. We can see here we have reflectivity horizontal, cross-correlation ratio, normalized coherent power, total power, mean dot-ball velocity, so on and so forth, down to differential phase. So, in actual fact, I'm running through the wrong notebook. I apologize. I got completely off track there. Sorry about that. Sorry for those looking at home. Can everyone open investigating the PyART Radar Object Notebook now, please? I knew I was missing a step. And as you can see, the reason why I got confused is the first couple of lines are exactly the same. Everyone execute those first couple of lines till you get down to the dir radar bit.
Do we need to close the previous one?
No, just open a new one. Go back to the tab that had all those notebooks in there. Click on the investigating the PyART Radar object, and we should get up. So is everyone cool with that? Good. This annoying thing, add field, which is a method that allows us to add data to the radar, so on and so forth. So go down to this. So we want to actually look at what some of these data objects are in there. And again, what I said before still holds true. Almost everything is a dictionary here. So we can actually look at what the contents of the azimuth data value is there. So if I say radar.azimuth.keys, that will show us what's actually inside that dictionary there. We've got, looks very much like a netcdf file, looks very much like a CF Radial file. We have comment, long name, standard name, units, data, and axis. Part of the PyART common data model is all the data, all the actual arrays of whether it be the pointing of the antenna, the reflectivity values, is always stored in data. So if you want to get to the data, go straight to data. Now I can actually, so if I wanted to actually have a look at the standard name, I can run this line here, line number 5. The standard name for .azimuth is beam azimuth angle. So that's actually the azimuthal angle of the antenna as it's pointing around.
That little U before those are...
That tells me it's a Unicode string, which you don't need to worry about.
Alright, but wait, stop. So if I was looking at this, how would I know that it's radar.azimuth?
So again, if I go up and I'm investigating, I'm going to say print dir radar, I can see one of the things inside my radar object is azimuth. So I go down here, and you know one of the nice things about the Ipython Radar Notebook, it's got tab completion. So I can type azimuth there, and it'll complete it for me. I can go here, and I can actually see all the...
So each of these has a dot keys, each of these has a standard name.
Exactly. Or each of them at least has a dot keys, and you can use the dot keys to work out what's in it. So for instance, if I go radar.azimuth.keys, I can see what's in there. If I go radar.elevation.keys, I can see what's in there. If it's a well-formatted file you've read in, it should always have those in there.
Alright, so the keys is always there.
Keys is always there, because keys is a method for the dictionary. So that tells us what's inside the dictionary. So if I want to look at the standard name, I can see it's beam azimuth angle. Actually, if I go like that, I do radar.elevation. I can see it's now beam elevation angle, all very straightforward stuff. If we look at the data now, I can see it's actually an array. This is what we call a NumPy or numerical Python array. This is the standard data object we use in Python for doing math. It's a very, very fast implementation of a basically LAPACK. It's a C library underneath it that does very fast addition, multiplication, integration, differentiation, and it is really the key to linking what we do with PyART with the rest of the Python scientific community. So it has a variety of methods and data things in there. For instance, I can write radar.azimuth.data.shape, and I can see what the shape of that array is. And it's a 1 by 1196 array. So that's actually the number of beams that are in my radar volume.
Scott, can you comment within the line, or do you have to create a different cell as a Markdown?
No, you can comment within the line, so I can go boo there, or I can put different line in there. There's a way by comments.
Yeah, okay.
Yeah,
I just wanted to see if it was, okay.
And a comment is a pound sign in Python.
Thank you.
So now we're going to do some really basic plotting. So I want to plot out what my azimuth is as a function of time. Now I said NumPy or numerical Python gives us this very powerful array object. Matplotlib is our plotting library that we use to produce graphics. It is what it says. It was designed by a bunch of MATLAB users who wanted MATLAB-like plotting in Python. So for those of you that have used MATLAB, some of this stuff is going to look very familiar. I actually went from IDL to Python, so I had to learn that all myself anyway. So again, so remember we imported up here this matplotlib pyplot module as PLT. So I'm now going to invoke that. And the first thing I'm going to do is create a figure object of 15 by 8 inches, whatever you want to call that. It actually is meant to be in inches, but it depends on your screen resolution how big it actually comes out. So just think about it as an aspect ratio. So that creates this object F, which contains my plot inside there. The second line actually plots the data. So I want to plot radar.azimuth, the data, so the array that has all my azimuths versus the array that has all my times in it. So the time of the ray, where it was, the time at which it was pointing, at which azimuth. I'm then going to create an X label, and we can do string addition here. So if I have Bob plus cat, I end up with the string Bobcat. So we're going to do radar.time standard name plus a bracket plus radar.time units, so the units for time, and then another bracket. Same again in the next line for azimuth. So again, we're making really nice use of the metadata that all your translators and developers have actually gone and put in the netcdf file for you. So here's the plot here, and it's quite simple. I have a constant azimuth all the way up to 90 odd seconds, then suddenly it changes, and I have a constant azimuth up to the end of the file. We have this nicely beam azimuth angle in degrees on the y-axis, time in seconds since some number on the other thing, and so this is an RHI scan. So I'd gone, what have I done? I've gone down like that, moved to a different azimuth, and gone up like that. So you can play around with changing the limits and all kinds of things, the size, later on there. And again, I'm going to start to speed up a little bit now that we've gone through some basic comments and get you guys to run this. But the next line does exactly the same thing, but for the elevation data. So I'm going to run that cell. And again, I can see I go from 0 all the way through 90 degrees to 180 degrees. I then have a little bit of dead time in my elevation at the top as I change my azimuthal angle, and then I zip back around to the other side. This is a horizon to horizon RHI file. So we go through the top and around to the other side. And again, you could play around with putting strings in there, calling it Bob, doing whatever. I encourage you guys to interact. Now you can always go back and grab the original zip file and put it back in there. So now I'm going to really briefly introduce you to a Python loop. So in Python, actually many other proper programming languages, we loop over elements in a list or things in an object. So if you wanted to do a loop from 0 to 10, I'm going to create another cell in here, and I'm going to say let A equal range 10, oops, that's a syntax error there, print A, right, there's my list from 0 to 9, which was created by my function range, which simply creates a list from 0 to n minus 1. And if I wanted to do a loop, I can say for I in A print I. And now it's 0, 1, 2, 3, 4, 5, 6, 7. For instance, if I wanted to say A equals a string A and a string B, now it goes A, B. So if I have a list of things, if I say for I, whatever I want to call it, in that list, the loop loops over that list. So here we have this another thing we have in the Python Radar Toolkit common data model that will always be in there is a .metadata. .metadata contains everything that should be in the netcdf header. So the global level metadata, radar name, all the stuff that, from a minimal thing when you get a UF file and you have nothing, to a proper ARM file where you should have a whole heap of metadata about who created it, when it was created, what the version number is. So here, I'm going to say for my key in radar.metadata.keys. Now remember, .keys produces a list of all these addresses that are in my dictionary. I want to print my key, so the actual key that we've seen before, a colon, and the actual data that's in that metadata dictionary. And I run that, and I can see all the metadata that's in the top level of that radar object. So now what we're going to do, actually this next thing is kind of just a little bit of an advanced exercise to show you a little bit more plotting. So our radar object, to identify different sweeps in RHIs, different sweeps in, say, a PPI when you're doing a volumetric scan, to help you very easily isolate a single sweep, we have a bunch of arrays that describe the scanning of the radar. These are, sweep start ray index, sweep end ray index. So we already saw we had 1,196 individual rays in our object, but we have 2 sweeps, as we could see from the azimuth thing. So in this start ray index, and ray start index and ray end index, that tells me the indexes in that 1,196 where my sweep begins and my sweep ends. So we'll do a little bit of investigating first. So I can say print radar, and again you can take advantage of the tab completion here, sweep start ray index data, remembering data is always in data. So my sweep rays start, the start ray for my 2 sweeps is at 0 and 598. I can change that from start to end and I can see my first sweep ended at 597 and my second sweep ended at 1195. We use an n minus 1. Okay, so Python, n minus 1, 0 to n minus 1. Unlike, was it MATLAB that goes from 1? Which one's 1 indexed? And Fortran. Okay, there you go. Not Python. So for those that are coming across from that, it's going to take some getting used to. So what I do in this one here, this is a very simple example here, that instead of creating one plot, actually creates a plot of one sweep line, then a plot of a second sweep line, and changes color. So, and actually has a legend in there as well. I'm going to leave that for you guys for an exercise to go through, play around and fiddle with that. But simply you can see I've now labelled the sweep numbers there. Sweep number 1 in blue, sweep number 0 in blue, sweep number 1 in green. Now we're actually going to get down to the data in our radar volumes. This is what ARM calls primary measurements. Everything else in this file and data model is just describing, geolocating the measurements. The primary measurements are things like radar reflectivity, Doppler velocity, all the things we can see, our cold pools, freezing layers, dendritic growth, and all that kind of fun jazz in. The primary data measurements in a PyART object are always in dot fields. Okay, so when you want to get straight to the moment, go to dot fields. And dot fields is now, follow this, is a dictionary of dictionaries. So it has a dictionary for each of the moments, radar reflectivity or what, and inside those is a dictionary that has the data and the metadata. So again, you need to kind of learn by looking here. So first thing we're going to do is print radar.fields.keys, which produces this output here. So they're all the things I've got in my radar. Reflectivity, cross-correlation ratio, so forth. Now we're going to loop over those keys and print out what's in the dictionary. So in this case we're going to look at the standard name and the units here. So for my key in radar.fields.key, print out the key and grab the standard name for that field and the units for that field. So we can see here we have reflectivity horizontal in equivalent reflectivity factor in dBz. Cross-correlation ratio, standard name, cross-correlation ratio HV, and unitless. It's a ratio, so on and so forth. So, so the final little bit of this notebook, we're just going to do a very simple plot. We call it a p-color mesh inside matplotlib. We're actually going to look at the moments here. Not going to try and make an RHI or a PPI out of it. That's the next notebook here. So again, we create a figure object, plt.figure, fig size equals 15 by 8. Again, you can change that, make it whatever you want. You can play around with the fonts. Google is your friend here. You Google p-color mesh, matplotlib, Python, you're going to get a million hits that tell you exactly how to do these things, as well as worked examples. So I'm going to create a p-color mesh. My PC equals plt.pcolor mesh. The x coordinate, the y coordinate, which is the time, so x coordinate is the range, so the range from the radar. The y coordinate is the time of the beam. The z coordinate, which is the color mesh itself, is reflectivity horizontal. Again, always grabbing the data. So data is always in data. I'm going to put an X label in there like I did before, a Y label, and I'm going to create a color bar. And I'm going to map that color bar to the p-color mesh that I created, because I might have multiple figures in one file and go back and create new color bars. So, and I'm going to set a nice little title on it as well. So off it goes and creates my, where did it go? This one here that, as you can see, has two sweeps of data in it, and you can see this little kind of bar thing in there. That is, of course, when I was actually just doing its very quick movement around before doing the next sweep. So what we want to do, if we want to actually just look at a single sweep, we can use our sweep start index and our sweep end index to isolate a single one, and that's the subject of this next line here. You can see here, instead of doing the entire range, we do in numerical Python what we call slicing. Slicing means taking a bit of the data. in this case, instead of looking at all of my range data and time data, actually I look at all the range data because I'm only isolating it in time. I slice it from start index to end index, where I got that from radar.sweep.endRay_index and radar.sweep.startRay_index. And because my p-color mesh itself, my 2D data is 2D data, both in range and time, I only slice one dimension. So in the azimuthal dimension, I only slice it from start index to end index, and I have this colon there. A colon means get me all of the data. I want all of the range data. I just don't want a certain range of data. So I can go here, run this, and I end up now with a single sweep there. So if I actually wanted to say I only want to look really close into the radar, I could go to range here, and I can put a open square bracket there. And let's look from the 0th gate to, I don't know, let's say the 300th gate there, right? And if I run that, I'm going to get a syntax error. Not a syntax error, a dimension error. Because I shortened my range, but I didn't shorten the thing I was plotting. So it said, hang on, your x index is, or your x index is the wrong length for the x index of data you've given me. So I want to go back up here, and where I've put my colon there, instead of the colon, I want to have from, what did I say, 0 to 300. And boom, where are we? Now I have this kind of zoomed in version where I can see a whole heap of clutter nice and close into the radar. So you guys can play around, change all the information in there, change ranges, change sizes, and play around with that. That first notebook is really just a basic introduction to how the data looks in PyART. Fortunately, you kind of look at this going, oh, you know, I can kind of see how I'd want to go off and write my own code to plot a nice RHI or a PPI that looked like an RHI PPI. We've already done that for you. So,
is there anywhere where standard help? Let's say you're explaining that plot something that module.
So the way
again,
Ipython. Yes, you can Google it, but Ipython is awesome. One of the reasons why Ipython is awesome, I'm going to go back to my other one here. I'm going to write down to the bottom and create a new cell. And say, for instance, I'm interested in p-color mesh. I type plt.pcolormesh. There's two things you can do, right? I can just open my bracket and hover my mouse, and unfortunately that's not very useful at the moment. Or I type pcolormesh ? Run that cell, and I get all the how to run it, all the inputs there as well. So I can make that bigger. Tells me all the inputs to it there, what it does, what the arguments are, so on and so forth. So.
Was there a space?
No, you're just right up against it. pcolormesh ? And of course, if I go here and I Google matplotlib pcolor mesh, you can see I get some very pretty documentation in there. There's also, Matplotlib has some great cookbooks. So if you search for Matplotlib cookbooks or gallery here, you can see a whole range of things where they've done weird and wacky kind of plots, like putting dolphins on the back of a noise signature. I don't know. Okay, let's go through the second notebook just carefully now. So again, we're going to go as far as we can with this today, but there'll be, you guys can look at it later on. So again, we've got markdown cells, code cells. I can go through the first bits fairly quick. Let's import our modules. Let's get our data directory right, and let's read it into the Python radar object and print radar.fields.keys so we can see what fields we've got in there. So everybody's up to that? Everyone zipped through that? Good. So now we're actually going to get to some PyART helper functions, like how to plot an RHI nice and easily. So PyART has a display module, a display method, which is a module in pyart.graph.radar_display, right? So to start building a PPI plot, an RHI plot, a time, height, range plot, say from a Kaiser or something like that, first of all we want to create a radar display, just like we created a figure thing before from the PyPlot module. So I do that by typing display equals pyart.graph.radar display, the radar I want to plot up. So everyone execute that. I now want to create my matplotlib figure, same way I did before. My figure equals plt.figure, some fig size argument. And then plotting an RHI from anything you can read into your common data module is as simple as display, which we created before, which is linked intrinsically to our radar, display.plot_RHI. The moment we want to plot, the number here is the sweep number. So, you know, it'll return an error if you put it higher than the number of sweeps that are in a volume. And these are optional keywords here. The minimum and maximum you want to scale the plot for there. They're always handy to set because I'm using a cloud radar. Going up to 64 dBz really is not that clever. You know, if you're dealing with a CSAPR file, you're not going to see down to minus 40 dBz. So we run this one. And we have, bingo, in like 3 lines. Jonathan has prided himself on the small number of lines it takes to go from reading in radar data to creating a PPI. I think we're down to like 4 or something like that now, which is nice. So we can see here this is a RHI plot from the same data we're looking at in the previous tutorial, but nicely formatted now from our ex-SAPR from the North Slope of Alaska. We've got some nice little, not precipitate, or again, we can talk science later on, but clouds where the precipitation isn't reaching the surface, what looks like a nice shear layer in there, some clutter in an arc around here, and our color bar there. PyART looks after the axis labeling for you, grabs the metadata from the common data model, which comes from the ARM ingested file, labels everything nicely for you, even turns some of the underscores into spaces, which is kind of nice. So if you look at the documentation on the websites I showed you before, it's infinitely controllable. You can replace labels if you don't like them, so on and so forth.
And I presume, the actually calculates these.
It uses four thirds Earth radius is what it uses for doing the conversion from range and stuff like that to being X, Y, and Z. In actual fact, we use that in the third notebook. It stores the X, Y, and Z, so that's actually used. You can use that for when you want to actually work out, geolocate the gates later on. So that's a bit big. You know, Tropopause isn't at 40 kilometers in the North Slope of Alaska. We've got a heck of a lot of useless space up there. So this actually has a method. The display object has a method, set limits. And you can set ylim or xlim to actually trim and scale your plot there. For instance, I'm going to do a ylim of 0 to 6, and again that's in kilometers, to actually now go down and just look at where the clouds, precipitation, and clutter returns are there, right? And we actually can start to see we're getting down to the individual gate level. One thing I like about the p-color mesh object, the way it works, it renders what it calls patches. So the actual patches in the p-color mesh are gates. So there's no smoothing, no interpolation. You can get down to the raw gate level, so you actually see what it looks like.
Smearing on the right, because I'm just guessing the antenna is scanning faster than
where we go, the right here.
Right, yeah.
Well, actually, you can see the block. The smearing isn't that bad, but that actually is the. It's not super sampling that much, so you're actually seeing the the elevation sampling there.
Because it's farther away from it.
Exactly right. Exactly right.
Okay.
In actual fact, as I said before, we can zoom right down to the gate level. So in this cell, we're going to not only change the X limits, but the Y limits. So we can see right down to individual returns around this cloud edge. And again, it looks so much cooler on your laptops than it does on these screens. But you can see the individual return. This is great for picking out where clutter is and stuff like that. So, and just for creating quick looks and stuff like that. So what did I say? Oh yes, so I remember what I did the next one. Okay, so this next kind of complicated cell is where we've used the fact that Python's a programming language and the fact that we've got PyART in there to make a quick script that gives us basically all the information we could ever want. about what's actually inside our radar object. What I do here is I'm going to create a list of lists. So a list that is going to be for an item for each row in my matrix plot. I want reflectivity, I want mean Doppler velocity, differential reflectivity, differential phase, so on and so forth. So if I looped over that list, the things I'll be looping over would be these pairs of things. So again, this will make a lot more sense when we execute it. So this is a list. Sorry, I found a mistake. That should be tuples, not yuples. So there's an object in Python. It's called a tuple. It's simply a number of things. So something that is a 2-tuple has 2 things in it. A thing that is a 3-tuple has 3 things in it. A lot of functions in Python return tuples. Instead of returning 1 thing, it returns 6 things. So I can say A, B, C, D, A, comma, B, comma, C, comma, D, E equals this function. Or I can, and that will return in A, B, C, and D a single value. Or I could say my big thing equals this thing, and it will return a 4-tuple that I can then unpack later. Again,
Is it like an array?
it's like an array, but it's a tuple. And I know that sounds funny. The difference is, it might be a list, but they have different methods. An array in Python is a mathematical construct. So you have .sum, .min, .max, .whatever. A tuple is a very simple list object. Okay? But you can use a tuple to create an array. But now I'm getting semantically philosophical. So
I want to add a key point that you can have a tuple that contains integers, floats, strings.
exactly, and that's exactly
Okay.
right.
An
Yes,
array
yes.
contains a single
Yeah.
base
Like, I mean,
object.
Okay, makes sense.
There's a whole heap of reasons why I gravitated to Python. One of the main reasons is it's also a programming language. So you can script some lovely things in Python you can't do in IDEAL because it has a lot more flexibility and a lot more diversity. So it's not. So for each one of these plots, I have a ranged pair, and again, that's a 2-tuple there. And yes, I could put a string in there, but then it'll kill it. And so what we do here again, we create a radar graph. For a single figure you make, you only need to create a display once. When you call that display, it does a lot of the background calculations, like the XYZ calculations, like ranges and string formatting, automatically, so it gets done once and doesn't have to be repeated, so you save on overhead. So now we're going to do a loop. We're going to do our loop over our field pair. So each time we hit that loop, we get a different, in I, we get a different field pair. So the first one was reflectivity, Doppler velocity, so on and so forth. The fields we're going to plot are those 2 field pairs. Read the comments in here. It basically explains every line what we're doing. This is now just a pair of strings. Range is just now a pair of 2 tuples. So 1 2-tuple per column we're going to do. And here is just a little bit of math we do. We're trying to work out what the size of the figure is going to be. And now we loop over the different rows. Long story short, let's run it. Because you've seen all that other stuff before when we did our formatting before. So now we have this nice figure here that has radar reflectivity, radial velocity, spectral width, differential reflectivity, differential phase, normalized coherent power, very good for isolating second trips, cross correlation ratio, really garbage looking KDP, forget the KDP that's in the ingested file, putting translator radar guy hat on, ignore all the KDP in the raw files, it's not configured correctly. We go through and recalculate it in the corrected moments, and Doppler spectral width there. So pretty neat, yes. So, and as I say there, yeah, KDP in the XAPA raw file is not well. But this helps you to really quickly see that. Again, in a very few lines of code, you can work out what's in my radar file, is it working, is it complete garbage. So now we're going to jump into doing some calculations in PyART, and actually, maybe doing some signal processing, eventually maybe even getting to some science. So the next couple of cells, and we're doing all right for time, not too bad. We're going to basically try to work out what's a valid meteorological return, classify that, and then save it back to our radar file. So again, I'm going to step pretty quickly through this because this just kind of gives you a taste of that, and we can explore these things later on, or you can email me because I kind of want to get to the saving point because that's kind of the coolest thing about PyART is bringing everything in from a common data model, everything in from a bunch of files to a common data model, but then from the common data model out to a properly formatted CF radial format file you can then use with radx, Titan, and all those other things. So we've tried to maintain community compatibility here. That's been our one of our biggest aims and one of the things we've spent a lot of time trying to do. So, okay, there are a variety of things we can classify a return off. And NumPy has this really nice where function. A lot of languages have a where function, but we can use where to create lists and locations of where a condition is met. So here, we're going to define a return, a gate, as being coherent if the normalized coherent power is greater than 0.5. Normalized coherent power, a little quick radar lesson, is the ratio between the non-coherent returns in the radar spectrum and the coherent part of the radar spectrum. Second trip, not coherent. If you're using a magnetron that randomly steps power. First trip, a lot more coherent, but there are caveats to that. So we're going to call something coherent if the normalized coherent power is greater than 0.5, and we're going to call it correlated if the cross-correlation ratio, ρHV, is greater than 0.8. So what we've done here in these two lines here, I've actually created an array using that line of booleans. The array is the same shape as my radar moment, but it'll have truths where this condition is met and falses where that condition is not met. Ditto for my is coherent, that's why I've called it is coherent and is correlated. And NumPy, numerical Python, has a whole heap of Boolean math that you can do with this. So is correlated and coherent equals np.logical and is coherent is correlated. All nifty. So we create 4 of these things that I'm not going to read out because that would take me way too long. And then what we do is I create a blank array. And the blank array is np.zeros-like. That means create an array that looks like normalized coherent power, but is initialized with all zeros. So it's a blank array, blank canvas ready for us to paint on. Now what I'm going to do is use the np.where function. np.where, numerical Python .where, simply when I give it an array of truths and falses, array of booleans, it returns a bunch of locations. And that's locations where that condition is true. So what I say, well, my blank array of logical classes, where is correlated and coherent is true, set those values to 1. Logical classes, where is correlated and not coherent is where that is true, set that to 2. Where logical classes is not correlated and coherent, set that to 3. Is not correlated and not coherent, set that particular position to 4. I've now, yes?
So when you said basically it's a mask,
yes,
of an array that fits those criteria. When you further do those things, it keeps the same size of the array. And
exactly right. Exactly.
Okay.
It's just a container I'm slowly filling up with locations.
Okay. Okay.
So we've now created this number arrays by number of ranges array with all these locations, all those values in there. So this is cool. But now what I want to do, I want to get that data back into my common data model as a field. So to do this, again, remember we said that in our common data model, our fields are dictionaries. I'm actually going to create a dictionary now. So this is how you create a dictionary in Python. You use these little curly brackets. Start up with curly brackets, and you have the key you want to put it into, and what you want to put into that key separated by colon, comma, so on and so forth. So in my, look at that, in my data key, remember, the data always goes in the data. I put my logical classes array with the thing I just filled out. Units, well, it's kind of unitless, so I'm going to set the units to unitless. Long name, logical classifications based on ρHV and NCP SQ, it's a long name. And standard name, logical underscore class. Unfortunately, that's not in the CF conventions yet, but we'll work on that. Now, our radar object that we originally read our data into has a method. One of those methods is add field, and it takes as an argument a dictionary. So as soon as I call that, I say, oops, where's my Python error? I actually haven't actually run the cell before. Got to make sure I run that cell before. Now when I run that, yay, our radar now has a new field, logical class. Let's have a quick check. So now when I print radar.fields.keys, I can see up the top here quite nicely, I have logical class in there. So I've now added a new field to my common data model.